Okay, in part D it says, given the initial mass of the leaf is 7.5 grams, do you notice that this is the first time in the question they've told us the initial mass? It's been unknown in part A, in part B, and part C, but finally we know what it is. Then it says, calculate the mass of the leaf after 10 days. So we go back to our equation and we write it down. So M, remember, is the mass of the leaf at any time t. That's equal to M0, but we now know that the initial mass M0 is 7.5 grams. So that's 7.5. And then that's being multiplied by e to the minus, its power is negative. And then k, we replace it with its value we worked out in part A. And then obviously t sits outside the brackets, but it's part of the power of e. So, calculate the mass of the leaf after 10 days. So we're just going to chuck in t as 10. And again, at this stage you can just go straight to the calculator and just type it in carefully using your brackets. Okay, so type it in carefully, and that's going to give us 0.48112. And then again round it to 3SF, so the mass of the leaf after 10 days is going to be 0.481 grams, and that's to 3SF. Okay, part D. Part E. Part E says, sketch the graph for the mass of the leaf with respect to time t in days. So part E. So our vertical axis is the quantity in the question. The quantity in this question is the mass of the leaf. So mass of leaf M, and the horizontal axis is always the time, and the time t here is in days. So the equation represents exponential decay, so the leaf's mass is decaying over time. So it has an initial mass M0, which is 7.5. We're told that in part D. So its initial mass M0, 7.5. And then as time goes on, its mass decreases exponentially. So the graph that represents that will look like that. Now, the graph will not touch the horizontal axis. So the horizontal axis will be an asymptote for the exponential decay graph. Now, that actually leads nicely into part F. Part F says, will the equation hold for large values of t? Comment on your answer. The answer is the equation will not hold for large values of t, and you can see this from the graph because we've modelled the situation with this graph. Now this graph will never touch the horizontal axis. So in other words, the mass of the leaf will never be 0. But in reality, the mass of the leaf will disappear. It will become 0. So this is a limitation of the graph and also a limitation of the equation here. That's why this is called modelling. We're trying to model a situation in real life as best we can. It's not going to be perfect. So in part F, the answer is no. The equation will not hold for large values of t. So it's no. Because from the graph, the graph will never touch the horizontal axis. And therefore the mass of the leaf can never be 0. However, in reality, the mass of the leaf will be 0. And that's it.